Without further ado, let me introduce you to our guest speaker, Mr. Paul Hollingworth. He had Durham physics and engineering alumnus and who graduated in 1985, and I believe you're from Collingwood College. Is that correct?
That's right.
Yes. So he's worked in the semiconductor and chip industry for many decades. So I'll hand it over to you, Paul.
Yeah, many decades. This is going to make me feel very old. But actually, I remember my time in Durham exceptionally well and enjoyed it a very great deal. So I'll talk a little bit about that. But the topic of my talk today is the chip industry, which you can think of as the world's most incredible machine for doing shrinking. And I'll explain why that is. So, sorry, bear with me. Basically, the chip industry, if you're not already aware of this, has really driven the world and since the 1960s. And you can argue that there's been three great revolutions so far in human history. The agricultural one, where people stopped moving around as nomads and trying to hunt animals and started sustainable agriculture, which coincided with, when writing evolved and so on. And then the Industrial Revolution, mechanization, machines, and then the information revolution. And the entirety of the information revolution has been driven by the evolution of the chip. So whether or not you're aware of it, it's chips that actually drive every aspect of this, from computers and the web through the supercomputers that we all carry in our pockets these days, through the higher definition displays, which are actually massive arrays of transistors, if you're not aware of that, and so on. So all of this is really only possible because the chip has evolved. So I'll give you a little bit of history, because I'm old and we always have to give a bit of history. And then I'll talk about the most important thing in the industry, which is called Moore's Law. And I hope some of you are at least aware of that term, but I won't be surprised if you're not. It's very important. And then I'll talk about making chips, how we do it. And then because this is for a graduating class or a university class at least, I'll talk a little bit about careers as well. So just a word about me. Yes, I was born and bred in the UK. I did a degree in physics and electronics, graduated in Durham from 85, and then I did a master's in microelectronics and management, which was an unusual course, very, very intense. We didn't get a lot of sleep, but we did actually design a chip, and I'll come back to that later, but this is in fact the chip that I designed back in 1986. Don't ask me if it worked, but I did design it. I started then doing work for the company that had sponsored me in engineering, which basically was doing chip design, but more importantly, you were helping other people who knew about electronics, how they could turn that printed circuit board full of electronics into just one chip. And that was a big thing in the 80s and 90s, still is actually. And then from there, my career moved into supporting the software to do that, and then the technical marketing, and then management, and so on. I moved to Germany for 5 years, which was fun, very interesting time. And one of the things about this industry is, like several, it's very global. So you do get the chance to work overseas. And in fact, I moved to Silicon Valley in the US for work reasons. And my wife and I thought we'd come across for 2 or 3 years, and we're still here. That often happens. California is a tough place to leave. I joined a startup in 2009. In fact, I've joined a few different companies over the years, but I wanted to highlight that one because it failed. And frankly, they usually do. So that's another common Silicon Valley startup culture kind of thing. But I'm now at a chip company, which is called Indie Semiconductor. We do chips for cars, automotive electronics. And we're growing fast, and actually we're about to go public next month, I hope. So that should provide us with some good funds to do some cool new things involving artificial intelligence and radar and LiDAR sensors and so on. So let me talk a little bit about the history of this. So I'm talking about chips. What are chips? Well, if you go back further, like to the 19th century further, a guy called Thomas Edison discovered something called thermionic emission. And a few years later, a guy called Fleming was able to create a valve. These big glass things, you may just have seen them in old hi-fi. And in fact, new hi-fi sometimes uses them as well. But valves are basically a thing that's about this big, and it's made of glass, and it basically contains a switch. And that's the point about valves, or tubes as they're called over here. They're the beginning of electronics, because you can either use them to amplify a signal or to switch something on and off. And so the first computers, the first one you'll probably read about if you look it up, is called ENIAC, because that's in the US. But actually, the first one was in Britain, and it was called Colossus, and it was built in the 40s. It was very secret at the time, because its task was to crack the German U-boat encryption known as Enigma. But ENIAC is considered the first true general purpose computer. It had 18,000 of these valves in it. It weighed 30 tons. It consumed 200 kilowatts of power, and it ran at 5,000 instructions per second. So it could do 5,000 basic additions, subtractions, that kind of thing per second. Remember that number, because we'll come back to that, 5,000. Then in 1946, three very smart gentlemen who were working at Bell Labs invented the transistor. Now, a transistor is like a solid state, very, very small version of the valve. And the thing under the bell jar there is meant to be one of the very first transistors, or at least a copy of it. They don't really look like that. And in fact, if you take out your smartphone, there are many billions of transistors in that smartphone, in any smartphone nowadays. And transistors are much better than valves because they're lower power, they're much more robust, they're smaller, they're faster, they're cheaper, and they don't really produce much heat. So they more or less immediately started replacing valves everywhere. So that was really how radio, TV, early computers. A friend of mine at Durham had an old car, and it was an old car. And it actually had a car radio with valves in. So you'd turn it on, then you'd have to wait for a couple of minutes for any sound to come out. So that's why they're not very practical. We like things to happen more quickly than that. So the problem with transistors was they had to be connected together. And this was during the days of the Apollo program. And people were building rockets, and actually joining these transistors together, you wanted to do it in as small a space as possible to make the circuits dense, but you couldn't get in there to do it. And bizarrely, they had a situation where women were highly prized for doing assembly because their hands were smaller. They could get more close together and do more transistors in an equivalent space. But in the late 50s, two different people independently invented the concept of joining transistors together on a single piece of silicon. So Jack Kilby at TI was the first to do it, but Robert Noyce of Intel, he was the first one to make it monolithic. So in a single piece of silicon, and this diagram on the right here is one of the very, very first things ever produced. That is actually an integrated circuit, and all the circuitry in there is built in, but also all the connections are built in. Whereas in this one here, which is Kilby's, you'll see there are external bits of metal doing the connection. So the promise of this was immediate, and so lots of companies started manufacturing them, and this was driven by the Apollo program, the race to the moon. And back in 71, a guy writing in Microelectronics News called the area Silicon Valley for the first time. And that's really been the center of this stuff ever since. Coming on to Gordon Moore. So I mentioned Robert Noyce already. He was one of the two founders of Intel, and he was the inventor of this whole integrated circuit process. And his great friend was Gordon Moore. And Gordon made an observation in 1965 that became one of the most famous things in technology. It's called Moore's Law. And it's just that because of the fact that you can make the individual transistors smaller, you can pack more and more of them on a chip. And every time you make the linear dimension √2 smaller, then you get a quadratic effect, so it doubles the number of transistors on the chip. And he thought that this was pretty cool, and he thought it might continue for 10 years. That was in 65, and it's actually continued ever since. So it's now through 20 generations of improvement. And on the right here is, this is actually from Wikipedia, but this is from Intel. And Intel, their first process was in 10 micron. And currently the leading edge chips are in 5 nanometer. That means the smallest feature which can be drawn on the silicon. And this is a true geometric progression. And I'm sure you've studied geometric progressions, but it's really hard to grasp the cumulative effect of these if they go on for a while. And I was telling Sarah and Hannah, there's this thing called the story of the vizier or the sultan and the chessboard. And it's a thing which is used to explain geometric progression. So the story goes that some ruler of a Middle Eastern country had some huge favor done for him by his advisor. And he said to him, you can have anything you like, half my kingdom, daughter's hand in marriage, all that kind of thing. And the guy said, well, I'd like a chessboard, please. Chess had just been invented. And I'd like 1 grain of rice on the first square, 2 grains of rice on the second square, 4 grains of rice on the third square. And the Sultan laughed and said, is that it? He said, yeah, that'll be fine. So the Sultan laughed and called for a chessboard and a bag of rice. And he got to about square 12 and the bag ran out. And then they had to bring 2 bags for the next square. And then he began to grasp the scale of the problem. And it turns out, if you work this out, that if you were really to do that, you would end up with about 18 quintillion tons of rice, or something like 2,000 years worth of annual modern production. So that's what happens with a true geometric progression. Now we're only at generation 21, but that's a lot. The first chips had just a few transistors. Now we have, as you'll see, tens of billions per chip. And each time they've been getting better, faster, and cheaper. But I will say it's getting harder and harder to continue. And the Moore's law demise is continually predicted. In fact, when I was at Durham in '86, I was doing a class, and I was told it was very unlikely that Moore's law would continue past 1 micron, and that's here. So since then, we're 1, 2, 3, etc. All these generations past 1 micron, and it's due to some of the incredible advances that have been made since. But okay, fine. So that's remarkable. But how are chips made anyway? A lot of people aren't really aware of this. So a chip is made from a single crystal of silicon. It's incredibly pure, 99.59 pure, with almost no defects in the lattice. So silicon is this regular lattice structure. And what we do is deliberately diffuse impurities into the structure. So this is silicon. So it's a tetravalent compound, has 4 legs, 4 bonds per atom. And in this case, here we might have taken phosphorus or arsenic. There is an extra leg. So there's an extra spare electron floating around. Or if we dope it, as it's called, with p-type compounds, like boron, for example, then there's a missing electron. So there's a hole into which spare electrons can fall. And the combination of the n-type doping and the p-type doping, when you stitch them together, that's basically how you make transistors. I don't have time to go into all the detail of that, but it's a fascinating thing in and of itself. And so what happens is we take this kind of wafer, silicon wafer, we grow oxide on top, which isn't very hard, just expose it to the atmosphere, you grow oxide on it. And then you go through approximately 300 different steps to build up all these layers, first within the silicon, because we're diffusing these p-type or n-type compounds in there, and then building up the metal layers on top. So this is a cross-section through a fairly modern chip. And what you're not aware of is this tiny thing down here at the bottom, that's actually the transistor. So that's half the job, just making those. And then the rest is making this incredible array of metals that's used to connect them. Remember what I said about women and small hands and transistors? It's like that to the nth degree. You know, we want to stack as many connections as we possibly can today so we can force the transistors as close together as possible. So you build up enough layers with different chemicals and metals and you get the chip. And if there's a particle of dust or contaminant, then they're completely ruined. So they're built in special factories called fabs. And a fab has to be about 10,000 times cleaner than an operating room, or basically none of the chips work because each one ends up with these particles of dust and doesn't function. A modern fab, there's not that many of them now, costs about 5 billion and only lasts a few years. So it's a difficult thing to do. And you may have read in the news recently, the entire world is being kind of held to ransom by these fabs who are out of capacity. And all sorts of companies are going lines down. They can't continue production because they can't get enough chips. Initially, they were mostly built in Silicon Valley, but now they're nearly all outside the US. Primarily, the three big centers are Taiwan, Korea, and China, with some in Japan. But they're sort of like the printing press. The fabs themselves are churning out the prints. The real design work is different. And that's where it's a bit like the difference between an author and a printer. You know, the author is the person that is actually coming up with the ideas, but the printer makes it generally available at a sensible cost. So this diagram just talks about some of the technical challenges to do this scaling for Moore's law. So when I was at Durham, in fact, this chip is based on a 5-micron technology. So the smallest length that we could draw on there was 5 microns. If you have the latest iPhone, as I expect some of you do, you have a processor called the A14 in there, and that is based on a 5 nanometer process. That's 1,000 times linear smaller, which means, of course, 10 to the 6 in density. And all of this is possible because of the way that we draw the patterns on the silicon, and it's done with light. But it's an interesting challenge because I mentioned 5 nanometer. So that's the smallest feature we can do. So how do you draw a 5 nanometer straight line? And what would you do that with? And that's actually a really interesting question because the wavelength of the light that is used for these things is typically 193 nanometer. And that's just the smallest wavelength you can get for ultraviolet light that you can produce reasonably. So that's a bit like saying, I'm going to draw a detailed, tiny little caricature picture, miniature picture, but I'm going to do it with a 15 centimeter brush and I'm going to be wearing boxing gloves. So it's a fairly extraordinary thing that it is possible. And you can sort of see in this diagram here, this only goes down as far as 11 nanometers, but I like the diagram. These are the wavelengths of red and violet light. And then just to scale, you've got a bacteria, a sperm cell, a red blood cell, that's this gray thing, and then a virus. So you can see we're actually down at the scale of virus levels, which is quite spectacular. And the net result, regardless of all the clever technology and ideas, is this. So what this represents on a log-lin scale, timer on the bottom, and then transistor count, is just how extraordinarily straight this Moore's law progression has been. And this goes from 1970. The Intel 4004 is generally reckoned to be the world's first microprocessor, all the way up to some of the latest AMD and NVIDIA processors, which have, now north of 10 billion transistors on a chip. Okay, so lots of billions and so on. But so what? What does that actually do for you? Well, it's quite interesting to look at the effect on the fastest computers. So twice a year, they publish a list of what's called the top 500 supercomputers on the planet. And this graph here is the latest. And what the lines represent is the blue is the total of the 500. What happens if you add them all up? What's the maximum performance that you get in operations per second, floating point operations per second, flops? And then the red line is the top of the list. It's the fastest computer on that list. And then the yellow represents what's the number 500 on the list. What does it take to get on the list? And the numbers here are fairly staggering. So do you remember I mentioned right at the beginning with the valve computer, ENIAC, 5,000 instructions per second? That's not the same as a floating point instruction. So call it about 1,000 ops versus the current top of the list, which is a Japanese supercomputer called Fugaku, and that's 442 petaflops. And I'm sure you're all familiar with the arcane names that happen after you go mega, giga, tera, and so on. Peta is the next one. After that, we get into exa. A friend of mine is part of a committee on Silicon Valley because it turns out that 10 to the 38 doesn't have a name yet, and he wants to call it Hella. So he wears T-shirts with Hella. I like the idea of a hell of a lot of flops, but anyway, we'll worry about that when we get there. So Fugaku is this many times faster than ENIAC was, and that's a direct consequence of Moore's law and chip scaling. So the achievements here are fairly staggering, and your smartphone is a great example. It has about 300 million times the same performance that the Apollo guidance computer had when they built that to go to the moon, which is a fairly extraordinary number. So one of the effects of this is how on earth do you deal with that kind of complexity? And a good analogy I heard while at Durham, actually, was it's kind of like a map. So imagine each transistor is a house. If you have hundreds of transistors or thousands of transistors, it's possible, for the human brain to grasp that. And that's fine. 50 billion, that gets a little tricky. That's like several planets worth of houses. So complexity management is really a major challenge, and we need new ways of handling the design for every time we change order of magnitude. So when I was designing, I actually found this. This is the chip plot for my design at Durham. And I'll just hold that up. I hope you can see that. So these are the sort of attachment points for the wires. And down here, I can't zoom in on this, it's a piece of paper, but you can see that each of those is a transistor. And I could pretty much grasp the complexity of that. It wasn't very, very hard. There's a few thousand transistors. But the modern ones, as I say, are in the billions. I was quite pleased I found this. It did get me into trouble. I had some area to use up. And I figured out, well, given how big this is, if you exposed it afterwards, you'd be able to see a big enough feature with the naked eye. So I put a large smiley on there with its tongue sticking out. And the Science and Engineering Research Council, who were objecting to this because they were paying for it, and they made me take it off. But they didn't spot the little hello mum one down the bottom there. That is actually, if you look at it with a microscope, that is actually in this chip. I know it's juvenile, but what the hell. So this complexity management thing is a big deal, and large companies in the computer-aided engineering and electronic design automation space exist just to solve that problem. It's a big focus of software research. The ideal is you describe the chip into the microphone and the robot arm hands you the chip afterwards. That's not going to happen anytime soon. Bugs. Bugs are an interesting thing. Bugs are a real problem, and debugging things is arguably much more work than designing them in the first place. But I came across this, which I thought was amusing. This is, technically speaking, the world's first bug, not the world's first insect, but it was the first thing that got called a bug. And this page on the right here is actually from the notebook of Admiral Hopper. And Grace Hopper was a big figure in programming. And she was one of the first users of computers. And the computers in those days were sometimes valve, but sometimes they were electromechanical. They used relays, actual physical switches. And one day their computer stopped working and she went between the racks to try and find out what the problem was. And there was a moth stuck in the relay. And so she took it out and stuck it in her notebook. And that, believe it or not, is where the term bug comes from. So education, of course, like everything else, has changed massively as a result of all of this. I think of my time in Durham as not that long ago. You would probably disagree with that, but to me, it doesn't seem like that long ago. And frankly, there was no internet then, really. There were certainly no mobile phones. We used libraries. We had encyclopedias. Information was hard to find. Access was limited. And therefore, you really had to try and learn facts because they sort of mattered, because otherwise you'd have to go and look them up again. Nowadays, of course, you just Google everything. So the internet's connecting everything. We're all increasingly used to instant access to all information and everywhere. And search giving you, instant results of that. That is an extraordinary thing. And again, it's entirely driven by the fact that all of these data sensors and Siri and Alexa and all of those things, I'll probably set all your devices off now, basically is all driven by chips. Communication, same thing. I used to call that Hollingworth had 2 wings in those days, and it had 3 payphones per wing, and there was always a line to make calls home. So a bit different from now. And then I think another good one is music, photos, and movies. So we had cassette tapes, then we had vinyl and CDs and laser discs, and now everybody just streams everything, right? Because why would you bother storing it? So I think you would be extremely aware of the now situation. You might not be aware of how different the then situation was and the vital importance of the library back in the day. It's funny, actually, when you go and look at colleges, they still talk about their libraries and how significant they are. My younger son is at Cornell on the East Coast in the US, and they're always talking about their library. I don't think he cares. Anyway, in careers, the chip industry is quite comprehensive. It's about solving all sorts of different challenges. Some of them are physics, chemistry, maths, nanotechnology, all sorts of engineering, software and complexity management, as I mentioned. And, this is all predicated on continuing to deliver this geometric progression of Moore's law. It's hard. It's really hard. I've been doing it for a long time now, and it's definitely only got harder. It's got more competitive, but it does mean it's rewarding. You do feel as though you're making a difference. When you see your relatives using technology that you've been involved in some way, that's extremely rewarding, very stimulating. So I recommend it. And, it's not changing at the pace that it was when it was reinventing the entire world. But I think it will continue to have a major impact, and I'll show you some examples. All sorts of different kinds of jobs. I remember when I was at Durham, I didn't really have any idea of what you would do when you went out into the world and got a job. So I'll tell you, there's a variety of different things, some of which are theoretical, if you're really smart and really like the theory. Then there's a lot of technical, practical stuff. So electronics, mechanical engineering. Software is now the heart of everything because everything has computers in, chips. So we use that in simulation. One of the things I was shocked by when I got my first job, I had worked in my my summer holidays, at a research establishment, and I had soldering iron, and I was, putting wires together, building circuits. And when I went to my first chip company, there was just a giant computer in the basement, and everything was done on displays. So it was all done through simulation. And that's probably a familiar concept to you now, but it's quite different. A friend of mine's a professor at Caltech, and she used to have to spend lots and lots of nights up on mountaintops and telescopes. Nowadays, she just does it from the warmth of her home whenever she feels like it, because it's all computerized. So some of the challenges that still exist, there have been times in history where people got it very badly wrong. T.J. Watson was one of the very first bosses of IBM. And in terms of famous last words, his will go down in history. He thought that by the year 2000, humanity might need 5 computers total. So he was a little off there. But some of these things we think will continue over a long time. So power, for example, I don't have time to go through all of these in detail, but power systems, solar power is huge now, and wind power. Big problem is if the sun's not shining or the wind's not blowing, you lose power. So power storage is a huge thing. So you may be aware of the Tesla Powerwall and others, gigantic batteries that go on the side of your house and store the energy. But it doesn't have to be electrical power. You could do it with compressed air or other technologies for actually storing energy. It's also very important at the other end to increase the efficiency, because as more and more things become battery powered, efficiency really matters. And transistors leak, and the smaller they are, the worse they leak. So stopping them leaking, finding ways to stop them leaking is really, really important. And a lot of the industry is working on that. I expect most of you learned to drive. I expect most of your kids won't bother, because they'll be riding in autonomous vehicles. And that is a real thing. And my company is very involved in that right now. We make the sensors for what's called ADAS, which is the driver automation systems. And then ultimately these will go to autonomous vehicles, which basically drive themselves. And this is already happening in constrained environments. So you can get a Google, or a couple of other companies are doing this now, Baidu in China. You get in, there's no driver, it will take you from A to B, but it's pretty constrained. It won't do it in the middle of Scotland in a snowstorm, for example. So AI is now going into everything. There's some interesting questions there about, okay, so an AI chip decides to do something. How do you know how it decided? I mean, you can't actually get a human to tell you how they decided on something either, at least not honestly. But it's going to be very important for AI. Today, we have what's called narrow AI. So AI, which just does one specific task, like image recognition. General AI, which is real intelligence as we understand it, is a long way further out. And there's a lot of debate about whether it's even possible. But if it is, it'll be microelectronics that makes it get there. And then displays and solving the continued problems of silicon scaling, the so-called Internet of Things, security challenges, and so on. The one thing I will say is I think that the next big revolution in humanity is going to be the gene revolution. And I'm sure you're familiar with the term CRISPR. CRISPR is a genetic technique which has been invented in the last few years by a lady called Jennifer Doudna and others, a Nobel Prize winner in University of Berkeley, University of California at Berkeley. And that is going to be a really big deal. That's the other big storage unit of information. You have the bit and you have the gene. And that's going to explode. It's going to be a huge deal over the next 20 years, but all of the implementation of that is going to be based on microelectronics. So chips will drive that as well. So one of the things that I discovered at Durham was I learned a ton of stuff about physics and maths and science in general and so on. And that was great. But I didn't learn a lot of other things there. It's a short time, it's very compressed. And so what I tried to do is to extract just a few things I wish I'd known when I was where you are now. One thing I'll say is that the ability to do a science or engineering degree is incredibly valuable. because it applies across almost anything. And you'll see this, in the city of London, the top finance jobs go to people with PhDs in physics, because they'll be able to understand any concept, no matter how hard. You're the top of the food chain from that point of view. And it guards your future employment, because frankly, anything that can be de-skilled over the next 30 years is going to be. Automation will take over wherever possible. So unless you want to end up saying, do you want fries with that? I think getting a science background and a physics degree is a very, very good thing to do. I hope that you've all learned some software. It was optional when I was there, but I think because software is now woven, computers are now woven into everything. The ability to code is kind of the vital skill for this century. One thing that I've noticed is that communication skills are rarer in science and engineering than technical skills. They don't come naturally. You should have seen my first attempts at presenting. They were lamentable. So you have to learn how to do it. So push yourself into situations where you have to do public speaking, and join industry. University committees. I ran the RAG week for Hollingworth when I was there, and I had the hardest thing I had to do was to stand up and bang the table in front of 300 people and get them to stop talking so I could make announcements. Scared the crap out of me. Join an industry that is growing, and join a company that's growing. It's much more opportunity there. You'll make more money, which is good, and you'll have a lot more fun. Most importantly, particularly early in your career, you want to have fun in what you're doing. You want to care about what you're doing, because you're going to be doing it for a lot longer than you study for. And some people ask, well, what about big versus small companies? I've worked for both. They both have their advantages. They both have their disadvantages. But I would always recommend starting with a good big company, because they're good at training. They'll move you around into different areas, different departments. My older son started working recently for Microsoft, and he had a couple of much smaller opportunities, and he chose Microsoft partly because he knew they'd give him a really good background. But once you've done the big thing, try a small company if you care about making a difference. Some people don't. They just want to work 9 to 5, go home afterwards, live the rest of their life. But for those of us who are interested in learning, interested in knowing things, as I suspect most of you are, because why do we do physics? To learn how the universe works, right? So in that case, you probably care about making a difference, in which case I'd recommend trying a smaller company as well, because you have much more of a chance to make a difference. And this is a modern thing. Try to choose companies that offer equity, by which I mean not just your pay, not just bonus, which may happen in some companies, but offer stock options and things like that. I worked for a company fairly early on in my career that offered stock options, and I didn't know what they were. And 2 years, and so it certainly didn't affect my decision. 2 years after I joined, I was making more money on a monthly basis from my stock than I was from my salary. Didn't continue, but for that period of time, it was really very nice. Helped me to buy a house and so on. So that is definitely a good thing. And this is connected back to what I said about joining industry and companies that are growing and doing well. If they're not growing and not doing well, then the stock doesn't really matter. And then the last and perhaps most important thing is it's all about your network, your personal network. I don't mean which flavor of Ethernet you're connected to or Wi-Fi. So build up a network now. The people you meet at Durham, some of them, I hope, will be friends for life. Certainly mine have been. Some of them will be very useful to you later in life. Maybe they'll make good connections for you. But start it now. Build your contacts. Use LinkedIn. That's kind of like Facebook for grown-ups, and things like that. So I'll just finish by saying I absolutely loved my 4 years in Durham. And after leaving all that time ago, I still think about it a lot. As I mentioned, I'm still in touch with some of the friends I made there. I'm very aware of the fact that you've had a much tougher time in the last year than most of your predecessors. Maybe not those who were interrupted by a world war or two, but yeah, it's been tough. And so I really hope that that things get a lot better this coming year. But I also hope you'll make the most of it. Don't forget the time there. It really goes very fast, and it is very memorable. And finally, this is my email address, paul@indiesemi.com. Feel free to shoot me an email, and I'll get to it when I can. And with that, good luck.
Wow, thanks for